Hello, students. Today we would like to talk about identities of the base A logarithm. We introduced the logarithm last lecture, and now what we want to do is talk about some of the properties that can make using logarithms and manipulating them much more easy and allow us to solve more complicated problems. So, as I said last week, what's a logarithm? It's a power of the base. And so we can utilize the toggle between the exponential and the logarithm to further our understanding of the properties of the logarithm. So let me share my screen. Now, what's interesting about the logarithm, as I've said before, as I repeated, is the toggle. That is, y equals the base A logarithm of x if and only if x equals a to the y. What's a logarithm? It's a power of the base. So the power of a that equals x is y. A to the y equals x. So that is the fundamental principle that we use for the logarithm. As I said last lecture, it's not the only way to define the base A logarithm. However, when it comes to solving equations, it is fundamental. It's what you're going to experience when you study trigonometry. There are many ways to define the trigonometric functions, yet we will begin with the unit circle, and that will provide symmetry in arithmetic and a means to solve many problems in trigonometry. So we can think of what we're doing with logarithms to be the foundation of what we are eventually going to do with the trigonometric functions. So what I've done here is I've summarized some of these properties, and we're going to talk in more detail about them. The first two sets are actually things that we've already discussed, the inverse equations. We know that the base A logarithm and the base A exponential are inverse functions. So when we compose them, the input equals the output. That is, in the very general sense, where we take the independent variable to be the same for each function, we have the base A logarithm of the function a to the x is just x. Input equals output. And also we have, if we raise the base A exponential to the base A logarithm of x, we get x. Input equals output. Now, we used some of these properties in the last lecture, and they were very helpful. Now what we want to do is explore some other identities that will make the solution of many problems much more realizable to us. Now, when I say identity, remember the definition of an identity. It's been a while since we've actually stated it. An identity is an equation that is true for all values of the variables for which it is defined. So it's a way to rewrite an expression that may be much more amenable to solving a particular problem. We find this to be the case when we're trying to solve equations, and equation solving is fundamental to mathematics. So the first three we will use often. That is, the base A logarithm of a product is the sum of base A logarithms. That is, when we take the base A logarithm of x times y, we can write that as the sum of the logarithms. Now, of course, we are making the assumption that the logarithms are well defined, and as you have different expressions, that tacit assumption will always be something that we assume. Again, we assume an assumption, right? But we will always keep that in the back of our minds when we're working with these identities. And of course, we're taking R to be a real number that we see in identity 3. I'll say more about that. And of course, A and B in this case are bases because we're going to have a change of base formula here. Now, an identity that is very close to the first one is the base A logarithm of a quotient. We know that we can write the quotient as just x times 1 over y as a product. So 2 is related to 1, and we get the base A logarithm of x minus the base A logarithm of y. So this is sometimes called, like I said before, the quotient rule. So the quotient that we have here parallels the product that we have here. So you could call this, if you want, I might as well just write that down. Number one, the product rule. And you could write for number two, the quotient rule. And while we're talking about it, we can go ahead and write number three as the power rule, and I'll speak to why we say that. Now, what we're seeing now is that when we take the base A logarithm of a power function, again, this can assume many forms. X could be fixed, and the power could be variable, and we would have an exponential function. So this can take on many forms, and x could be an expression other than just the variable x. But when we take the base A logarithm of x raised to a power, the power can then move to a coefficient status. That is, we now have a multiple. This is why we call this number three the power rule. It just allows the r to move into the front as a multiple of the base A logarithm. This rule is very, very powerful. And there's an example here that I will say something about that will utilize the power rule here. Now, what I would suggest with the identities is that you practice writing them so that you commit them to your long-term memory. That is, you want to be able to rely upon them when you need them to solve problems. So write them down frequently and make sure that you know them. Now, the other two here have to do with change of base. The fifth one I've already talked about. That is, when we change the base for a base A exponential, we can simply use the inverse rules here. That is, if we want to change to base B, we could just simply let now A to the x be the input of B raised to the base B logarithm of A to the x. And then, of course, input equals output. Now, one thing you notice here is that if we apply the power rule to A to the x can come down as a multiple of the base A log or the base B logarithm of A. So here, this x can just travel to the multiple status, be a coefficient of the base B logarithm. So the change of base for the base A exponential is very straightforward because it uses a property that we've already discussed. Now, for the base change with the logarithm, it's actually very straightforward and easy to remember. So if we wanted to write, in this particular case, the base A logarithm of x in terms of the base B logarithm, we simply do a cosmetic change. That is, we change the A to a B, and then we divide by the change of base factor, which is the base B logarithm of A, which you can actually see in problem or identity 5 right here. Okay, that's the change of base factor, so to speak. It's what allows us to move between the bases. And so when you get to calculus, you will find that the natural base is the base of calculus. And in order to transfer the calculus to other bases, we will just convert them to base E. So again, we won't have to do anything to these. We really won't have to do anything to these. We will have different ways to define logarithms in calculus, but these are all the same. Everything that we're learning will not change. We will simply have maybe more sophisticated ways to define things, but that's not going to undo anything that you are learning in this course. Now, again, like I've said before, these identities are extremely important. So write them down and make sure that you commit them to memory. They will be used much in this class, in the pre-calculus course, and also in the calculus sequence. And then, of course, as you continue in mathematics, you will use logarithms frequently. Just like the trigonometric functions, you're pretty much stuck with them. And just remember, the logarithmic functions, the base A exponentials, the trigonometric functions are termed transcendental functions. So they have some qualities that are very similar to the algebraic functions that we've spent much time with, but they also have properties that vary. But we need to know how to work with all of them because they are certainly the domain of the calculus that you will eventually study. Now, what I want to do is say a few things about one of the proofs here. These are not difficult to prove if you just use the toggle that we've set up. And I always say, what's a logarithm? It's a power of the base. So we have to utilize the properties of the base A exponential, which make our understanding a little less sophisticated, but certainly very useful. So when we look at the proof of the power rule, we first start with something basic. That is, we just let, in this particular instance, pick your favorite letter, let z equal the base A logarithm of x. Now, this just simply provides us a way to toggle. That is, if we would like to use the exponent rules or the power rules of the base A exponential, we must introduce that function. So now, what's a logarithm? It's a power of the base. So the power of A that equals x is z. So x equals A to the z. So this is fundamental. Again, this is the relationship between the base A exponential and the base A logarithm, which allows us to work problems. Again, it is the fundamental toggle, as I say, as we move between the two functions. Now what we can do is we can express x to the r here and then use the exponent rules for the base A exponential. So then x to the r power is simply a to the z raised to the r power. And then, of course, we can apply the exponent rules or the power rules for the base A exponential. So this gives us a, z, r. So the important thing here, again, is doing the toggle to transfer to the actual base A exponential and then express ax to the r as a power of A. And so we say x to the r is just a to the zr. Okay, now we go forward and now we go backwards. We toggle again. So if and only if, we'll now say the base A logarithm of x to the r is now the base A logarithm of a to the zr. Now, of course, you could avoid what I've done here, but I'm just applying the base A logarithm twice. Again, we could do the toggle and be done with this and just write zr, but we know this equals zr because these are inverses. So notice here, we're seeing, again, if you would have liked to have left this out, let me show you how you could have done that. The power of A that equals x to the r is zr. So zr is a logarithm. That is, zr is the base A logarithm of x to the r. But sometimes it's nice just to go ahead and apply the base A logarithm and save yourself a little mental anguish and just move this way. But it's the same thing. It will simply facilitate the movement from the exponential to the logarithm. And now, of course, we can simply just rewrite the z as our initial definition. So the base A logarithm of x to the r will just equal r times z, and then replace z with the base A logarithm of x. Now, this is very simple, but what we need and what we need to feel comfortable about is that we have a means to justify these identities with the definitions that we have constructed for the base A logarithm. And like I've said before, these particular identities are very flexible. We can certainly substitute different expressions for x. And of course, the x could be fixed. The r could also vary. So these particular identities are extremely flexible. We just simply have to apply them correctly as they are stated. Remember, an identity is an equation that is true for all values of the variables for which it is defined. So that opens the door to how we can utilize the base A logarithms very effectively later in the calculus. You might be surprised at some of the interesting calculations we can do. Now, I will say this. With most of the problems that we do in this class, we're going to try to combine log terms so that we can solve equations. The expansion of logarithm terms will be more the domain of the calculus, but we will practice doing both. Now, what I wanted to do was the example that I left on the previous slide, which was this one here. Let me just write it here as another example. We'll just go ahead and prove this, which is an interesting example about the natural logarithm. So we want to prove that the additive inverse of the natural logarithm of x minus the square root of x squared minus 1 is actually equal to the natural logarithm of x plus the square root of x squared minus 1. And this is not difficult. Now, again, what we want to be able to do is to use the power rule in any algebraic property. So when we use new identities, we certainly don't forsake all of the other structure that we know about algebraic functions. So we will have to use that in concert with the new ideas that we have learned. So now the proof is very straightforward. So we have, in this case, the left-hand side can now utilize the power rule. That is, we can take the negative here, the -1, and move it to the power status of the argument of the logarithm. This is what I was talking about before. The actual argument can have many, many different forms. And that's where the power of these particular identities is very, very helpful. So we have the natural log of x minus the square root of x squared minus 1 to the -1. So now, of course, the -1 can be written as the reciprocal. That is, we can reciprocate the argument. So we have the natural log. So we have 1 divided by x minus the square root of x squared minus 1. This is a common construction in mathematics. Now, in order to make this work, we are going to utilize a conjugate method that you will also continue to use in pre-calculus. So we're going to multiply by the conjugate of x minus the square root of x squared minus 1, which is basically replacing the minus here with a plus sign, upstairs and downstairs. So we're multiplying by 1, but in a fashion that will allow us to manipulate this particular problem to our advantage. So I do this in red so you can actually see the algebraic manipulation. So we've kind of left the domain of the logarithm identity to rewrite the actual argument here so it's more accessible. Now just remember the ln is the base E logarithm. So ln of x is just the base E logarithm of x. And we use this special notation since the base E is very distinguished in our mathematics. Okay, so now very nicely, we have a difference of two squares that's factored, and that of course will collapse. So we have the natural log of x plus the square root of x squared minus 1. Now downstairs, notice the outer and the inner absorb. They are additive inverses. So we're just left with x squared minus the square root of x squared minus 1 times the square root of x squared minus 1, which is just x squared minus 1. The 1/2 powers add. I'll go ahead and write that, but notice here we have a minus and a plus, so we've got minus the square root of x squared minus 1 quantity squared. And now, of course, the square will absorb the radical, their inverses. So we have the natural log of x plus the square root of x squared minus 1. And downstairs, we just have x squared minus the quantity x squared minus 1. So that's what relieves us of the additional powers of x. So, of course, the x squareds absorb, and we have minus the negative 1. So that just gives us a 1 in the denominator. So we're done. So again, notice using the conjugate method, what we see here is that the denominator just equals 1, and we have exactly what we set out to show. That is, by utilizing the power rule to move the coefficient here to the power status, as we see here, then a conjugate technique, we have conveniently showed that this expression is equivalent to this expression. So this is where the power of the log identities can be seen. And you will find this to be the case in mathematics. There'll be certain identities that are used over and over. And of course, the power rule is a very important one. And that's why I went ahead and showed you the proof of that. Now, again, just remember, you can prove any of these identities using the same technique. So I encourage you to look at that and just practice, just so you can keep reminding yourselves that a logarithm is indeed a power of the base. And that's what moves the problem forwards and backwards to whatever particular expression you need to move the logic forward. And we'll use the change of base too, and we'll use the other properties in some of these examples. The change of base is very useful if it's needed in solving equations, but like I said before, it'll be useful in transferring calculus when you take the calculus sequence. Now, in your homework exercises on Blackboard, you see some interesting examples like this that don't appear to be anything but academic exercises. Many times in mathematics, we practice particular techniques with problems that don't seem to particularly go anywhere, but they certainly help us to utilize the new methods. So what we've done is we've defined the natural, notice we're using natural log here, very convenient. We have the natural log of 2 is A, the natural log of 3 is B, and the natural log of 5 is C. And so what we want to do is rewrite the logarithms in terms of A, B, and C, where it's applicable. So let's look at the first one, the natural log of 6 over 5. Now, if you think about the identities that we just stated, this is the log of a product, which can be written as the difference of logs. So this is the natural logarithm of 6 minus the natural logarithm of 5. Again, the log of a quotient is the difference of logs. Very simple, not difficult. And again, apply the identities correctly. Make sure that you have everything correctly written so that you can apply them. The biggest mistake is the application of the identities when they are not set up in a sense. Make sure that you have set up the problem or you have an expression to which you can apply the identities. Just like working with algebraic identities, you are very familiar with these. Now, of course, the log 5 we know is c, so we're done with this, but now we can actually rewrite 6 as 2 times 3. So we'll have the natural log of 2, and I'll just use a dot there to emphasize the multiplication. It's not necessary, but I think it helps in the understanding. And of course, the log of 5 we'll just write as the c. And now, of course, we have the log of a product, which can be written as the sum of logs. So we have log of 2 plus log of 3. Again, these are very simple, but the simple is important because these are fundamental. And now, of course, log of 2 is a and log of 3 is b. So we get a plus b minus c. Like I say, these are academic exercises, but they're important because many times when you're working in mathematics, you will see ways to rewrite logarithm expressions. You might look in a textbook and see a very interesting expression that does not look like what you just computed. But then when you study the quality of the arguments, you're able to rewrite your expression as the one you see in the book. So this is very important so that not only can you further your understanding of the identities, but in rewriting the expression, you may glean other particular characteristics of the expression that were not available in a previous form. Okay, so let's look at 2. Here we've got the natural log of the cube root of 25. So what we can do in this case that might make it a little bit easier is we're going to go ahead and write the cube root as the 1/3 power, just like that. So now we have written the cube root as a power of 25, the 1/3 power. And now we can apply the power rule. So basically we have the natural logarithm of 25 raised to the 1/3 power. The argument here is this, and it is written as a power. Notice here the base is fixed and the power is fixed, okay? So we can apply the power rule. So this will give us 1/3 times the natural log of 25. Again, you may rewrite things in a different way, but the result will be the same as long as you apply the identities correctly. Now, of course, we're going to do the same thing we did in the previous problem. We can now rewrite the 25 as 5 times 5 and apply the quotient rule or the power rule, your choice. Let's just be crafty and do 1/3 times the natural log of 5 to the 2nd power, because 25 is 5 squared. And so now we can apply the power rule again. So we'll have 1/3 times 2 times the natural log of 5. But of course, 1/3 times 2 by definition is just 2/3, and the log 5 is just c. So we see in these particular cases that we get expressions written in terms of the letters that we have here. Very simple, but very useful in practicing the techniques. Now, the very last one shouldn't be a surprise either. We don't have a 24, of course, in the list, but we can certainly rewrite the 24 as 3 times 8, which will open the door to some of these numbers. So we have the natural log of 3 times 8. And that's good because we know we have a 3 up here, but now we can apply the product rule. So we have the natural log of 3 plus the natural log of 8. Now, as far as this goes, we know this is b, but we need to rewrite the 8 as a power of 2. We know 8 is just 2 to the 3rd power. So we have, b for natural log of 3 plus the natural log of 2 to the 3rd power. Now, of course, this is certainly not the only way you can do it. You can still get the same answer, but this may be the most efficient. And so now we have b, and let's apply the power rule. We have 3 times the natural log of 2. And now we can fill in. So we have b plus 3 times log of 2, which is a. So these are very simple, but the practice that we get utilizing the identities is the main point here. Again, we find that if we learn something new, and this is not always the case in mathematics, you may learn a new theorem, but your use of it may be very restricted based on the types of problems you're doing. So what often will happen is that we will work problems that don't seem to have a huge impact on our field of mathematics, but have academic impact. That is, they help us to see how we can actually utilize the given information by manipulating the arguments in an advantageous way. So what do we do when we actually execute mathematics, ladies and gentlemen? We look for patterns. Patterns are how we realize what we're dealing with. We see a certain pattern of a function and we categorize that function, and then we think about all the qualities and properties we know about that function. And then we execute the problem using those ideas. So again, practice the patterns that you see here so that you can learn these identities. They are extremely important. Now what we want to do is just a few more examples of how we can actually take expressions and unravel them. You noticed in the past example, we were unraveling the expression. We started with 1 logarithm and we expanded it. That's a good technique, just like I said, but often when we're dealing with equations, we want to take maybe 2 or 3 logarithms and compress to 1 logarithm. That is, bring the logarithms together. So let's look at an example of this. Again, we expanded in the last example. Now what we want to do, we expanded. Now what we want to do is take the expanded version and compress it. We want to make 1 logarithm. So here's an example. So we have the overuse of the natural logarithm. You can use any base you like, but I guess the author likes the natural logarithm. And I certainly don't mind it. It's a good logarithm. So if we have an expression like this, the direction would be the following: write as 1 logarithm. Now, of course, we could make the problem more difficult if we had to change the base, and I'll say more about that. So when you look at this, you look at this expression and say, of course, we could factor the argument if that turned out to be something that was needed. But this is ready to go. We certainly don't want to do anything to this. This is a log function. The coefficient here is 1. When we look at this part, we see we've got a little bit different thing going on, in the sense that if we want to combine these, we need a plus or minus here. So what we can do, if you think about this, is just move the -4 up as a power, and then apply, actually by the power rule, and then apply some basic algebra. So again, the idea is that there is no set way to work with compressing 2 logarithms. You simply apply the properties in a way that give you a mathematically correct execution. So let's do that. So we have the natural log of x squared minus 25 plus the natural log of x plus 5 to the -4. So this is where we get to use some of our algebra. Remember, we've used this before. If you have an expression x to a negative power, that is simply the definition of reciprocal, which of course can be written this way, if that happens to be a more advantageous way, which we will find many uses of in the sequel and also in the calculus. So we'll do that here. So we have natural log of x squared minus 25 plus the natural log of 1 divided by x plus 5 to the 4th power. Just like that. Just applying this identity. And now we have the sum of logs, which we can write as the log of a product. That is one logarithm. So now we have x squared minus 25 times 1 divided by x plus 5 to the 4th power. Now, I've written this out in a more extended means so that you can see that we're actually multiplying these. And now we can move the actual product together as one fraction. And notice we can go ahead and factor the difference of squares here to absorb one of the x plus 5s. So I want to write this out in full detail so you can see what's going on. So we have x minus 5 times x plus 5. And then, of course, downstairs, we can go ahead and write this 4th power as x plus 5 to the 1st power and x plus 5 to the 3rd power, just like that. And now you can see that the x plus 5s absorb. Again, an identity is an equation that is true for all values of the variables for which it is defined. So again, we're tacitly assuming that this is well defined, that we're not allowing x to be 5 or negative 5, so that this is a 0, which of course would be undefined for the logarithm. Remember, the arguments must be positive. They must be greater than 0 for the base A logarithm in the real sense to be defined. So now we see these absorb, and we've got a simpler expression. So we have, in this case, x minus 5 divided by x plus 5 to the 3rd power. Now, one thing you notice when you're doing online homework, the use of the parentheses is greatly enhanced due to the argument of the logarithm. But if you're writing, you can sometimes relax the notation and just get rid of the outer parentheses and know you're taking the natural log of x minus 5 divided by x plus 5 raised to the 3rd power. That would certainly be okay and is often practiced. But this is really what you're saying technically, in a technical sense. So if you feel more comfortable with this, that's fine. If you were to leave these out in your work, I would not be bothered by that. Just realize that whatever method you use, it has to be unambiguous. So we couldn't do this if we had a sum. For instance, this is fine, or like I said before, you could write this as log of x minus 5 divided by x plus 5 raised to the 3rd power. If you left out the outer parentheses here, I would know what you meant. So if this makes no difference to you, just go ahead and keep using this. So it's important to know that we're taking the log of this fraction. Now here, it's unambiguous because this is just one piece. So if we still include this, we would still understand that this would be equal to this, even if it didn't have the red parentheses. But here's an example that I'm talking about. Say you have the base 3 logarithm of x squared plus 5. Okay, that's clearly an expression where the argument of the logarithm is the expression x squared plus 5. So you could not write log and then do something like this, say x squared plus 5. You couldn't even write a sum either. I'll just write down several things that this is not equal to. You can't just, for instance, leave out the parentheses, because here this would be ambiguous, because it's like if you write something like this, you're saying, oh, well, you can just relieve the parentheses and write the base 3 logarithm of x squared and then just tack on the 5. That's clearly not correct. And this does not equal the base 3 logarithm of x squared plus the base 3 logarithm of 5. There is no what we call sum rule. We have the log of a product is the sum of logarithms, but there's no way to break down the sum to write something like this. So just be very careful that you do not do this. That's what I tell my students, that you want to be creative in your mathematics, but you want to be creative in a correct sense. So please do not just infer new identities from the ones that we have discussed. Something like this is not correct. But I'm just saying that as you write your mathematics, if you want to relieve yourself of some outer parentheses, this would not be unambiguous if you left out the red parentheses. But again, if this is no consequence to you and you're fine with the parentheses, keep using them. I think it's probably best anyway, because it cuts down on any level whatsoever of confusion. Okay, let's look at another one. Because when it comes to combining logarithms, we have a really, really good way to apply the toggle when we're solving equations. So this is important. Let's try another one. So we have the 2 times the base 10 logarithm. Remember, when we write the base 10 logarithm, we can leave out the subscript 10, and the inference is base 10. So this means base 10. LOG by itself is just base 10 minus 1/3 the base 10 log of x cubed minus 2. This is similar to the last one, very similar. But now what we want to do is, again, write as one logarithm. Again, these are very academic exercises, and in order to be able to use these properties or identities to solve equations, we need to know how to work with them. So the first thing I want to notice is we've got to use the power rule in both cases. Notice here, the argument of the logarithm is a difference. It's x cubed minus 2, okay? And we can apply, again, the power rule. Now here we have something a little different. It's still an expression. We have 3 times x cubed. So we can still apply the power rule to this expression. This is what I was talking about before. The argument can take on many different forms. As long as the basic pattern of the identity is present, you can use it. So in order to eventually combine these logarithms, we must have coefficients 1 or minus 1. That is where we would use the product rule with a plus, or we'd use the quotient rule with a minus. So in both cases here, we want to apply the power rule first to get rid of the 2 and the minus 1/3. So we have the base 10 logarithm of 3x cubed raised to the second power minus, or now we'll just plus, let's just move up the whole thing and practice our algebra, the base 10 logarithm of x cubed minus 2 to the negative 1/3. Now, if you will, you can go ahead and apply the square. So we have the base 10 logarithm of 3 squared times, and if you like, we'll go ahead and say 2 times 3, x to the 6th. And then we'll just write that as one piece as 9x to the 6th. And now plus the base 10 logarithm of 1 divided by x cubed minus 2 to the 1/3 power. Again, using the same identity we used with the last example. Now we have a product for instance, we have the product rule. That is, now we have the sum of logarithms, coefficients of 1, which we can now write as 1 logarithm in this particular direction. So we have the base 10 logarithm of 9x to the 6th times 1 divided by x cubed minus 2 to the 1/3 power. And now we can write this as one fraction. So x cubed minus 2 to the 1/3. So that gives us the compressed expression. That is, we write the 2 logarithms as 1 logarithm. Again, if you can combine 2, you can combine more than 2. For instance, if you have more, then you can just work on 2, combine them, and then work on the third expression, get it ready if you need to use the power rule, so you can then combine again. So the key to these problems is basically moving coefficients to powers so that you can use either the quotient rule or the product rule. And then, of course, utilizing basic identities for negative powers and then collapsing the expression. Now, of course, you can often leave out these types of steps, but it again shows you that you're multiplying this argument by this argument and then just collapsing it to write as one fraction. So maybe initially it's better to add more steps, and then you can feel a little bit more comfortable as you develop a more understanding, a better understanding of these new identities. Now, again, let me just say one thing before we talk about change of base. Say you had an example like this, where we've got actually 3 logarithms. So I'm going to say the same thing, write as 1 logarithm. You can see how these are going to be very helpful with solving equations. So say we have, I don't know, the base 3 logarithm of x squared minus 9 minus the base 3 logarithm of x plus 3 plus 2 times the base 3 logarithm of, in this particular case, we'll just say x plus 3. Just a kind of a interesting situation here where it looks like we should be able to combine these. I mean, we've got the same argument, but we've got a 2 here and a minus here. Okay, so let's see what we can do. Write as 1 logarithm. So first, we're done with this one. We may have to factor that, but if that need arises, but this one's good to go. And now we need to move up the negative. So we have plus base 3 logarithm of x plus 3. And of course, now we have the minus 1 because we moved the minus upstairs. Then plus base 3 logarithm of x plus 3 quantity squared. So we see we're going to get some collapsing here. But notice now, we've moved the negative up, so we have a power of -1. We move the 2 up, so we have a power of 2. Now we can associate. So we'll do these first. We'll associate the first 2 logarithms. So we have the base 3 logarithm of x squared minus 9 times, and now I'll go ahead and flip this. 1, I'll just leave out that step since we're getting pretty good at it. We get that because, again, we have the minus 1 here, plus the base 3 logarithm of x plus 3 quantity squared. Oh, let me leave room for the 3. 3 is important. Don't want to leave 3 out. There we go. So now we'll go ahead and finish this. We have the base 3 logarithm. We'll go ahead and factor this, x minus 3 times x plus 3 divided by x plus 3. So, of course, the x plus 3's will absorb, my favorite word. Always use boxes, make your work neat so that you can read it. Slash lines or slashes never work because they impede the understanding of your work, and you just don't need to do it. Plus base 3 logarithm of x plus 3 quantity squared. Now, let's just go ahead and reduce this. Base 3 logarithm of x minus 3 plus the base 3 logarithm of x plus 3 quantity squared. Now we're almost done. We just have the sum of two logarithms, which we can write as one. So we'll multiply them together. So the base 3 logarithm of x minus 3 times x plus 3 quantity squared. And that would give us a single logarithm. So now, depending on the problem, it may be that you would have to maybe multiply some of this, or this may turn out to be fine. It just depends on the nature of the problem. But notice what we've done here. Doesn't matter how many logarithms you have, the finite process can be done 2 at a time. So we have the base 3 logarithm of x squared minus 9 minus the base 3 logarithm of x plus 3 plus 2 times the base 3 logarithm of x plus 3. So just out of interest here, I just paired up the first two. So as we applied the power rule, here we're good to go. Here we move up the -1. So we have the base 3 logarithm of x plus 3 to the -1. And now we have the product rule. That is, the sum of logs is the log of a product. So we multiply x squared minus 9 times 1 over x plus 3 because of the -1 power. Okay, and then to finish this part off, the x squared minus 9 is just x minus 3 times x plus 3. So the x plus 3 is absorbed, and that gives us the base 3 logarithm of x minus 3. Here we've just been dragging this down the whole time anyway. And now we just pair these two. We now have the sum of the base 3 logarithm of x minus 3 and the base 3 logarithm of x plus 3 squared, which now we can write as the log of a product, and we're done. Now you can go ahead, like I said before, depending on the type of equation you have, you may have to do some manipulations here if it means expanding this and collecting terms. But the key here is at this point, we now have written the 3 logarithms as one logarithm. So even though there will be instances when you are interested in expanding logarithms, as we did earlier, most of what you're going to be doing when it comes to solving equations is doing the compression technique. So then you can apply the toggle. If it's required that you write the logarithm form in the exponential form, you'll have the one logarithm and give it, which will give you the ability to do it. Remember, we can always use one-to-one when it appears. You know, the equality of 2 base A exponentials or the equality of 2 base A logarithms. As long as the coefficients are 1, we can just set the arguments equal or the powers equal. That's very restrictive, but very useful when it appears and when that pattern is available to us. So just remember the compression technique will be very valuable when it comes to solving equations. Now, the very last example I want to discuss is the change of base. For instance, if you are working in a class where you need an approximation, that's not simple. For instance, if you have the access to base E or base 10, even on a Google calculator or a simple scientific calculator, and you need an approximation that basically takes you away from the exact expression, that would be fine because approximations are often necessary, especially for your clients who need a number, so to speak, that may not be as understanding of the exact notation. So if you have access to base E and base 10, but maybe not base 3 or base pi or whatever, you can always do some general estimating. But if you want a little more precision, then the use of the scientific calculator can be very, very helpful. So here's an example. And here's and the examples that I have are actually from your notes, which are very good. Say we had something really interesting like this, and you're thinking, how would I ever come up with this? The base pi logarithm of 5.3. Okay. Now, when you look at this, you know, pi is a transcendental number, 3.1416, etc. And so when you think of the base pi logarithm of 5, you think of squaring something 3.14, squaring it, you're going to get something bigger than 9. So you're thinking that the actual value here would be a number between 1 and 2. Okay, that's fine. And you can approximate that with the base that you have available. And say you have a base 10 log key on your scientific calculator, or you have a table of base 10 logarithms. So all you need to do is, again, change to base 10. So you have base 10 of 5.3. And then the change of base factor will be the base 10 logarithm of pi. Now that's very messy, but it's certainly a lot less difficult to understand than this. So now, if your client needs an approximation here, you can simply use your table and take the base 10 logarithm of 5.3 and divide by the base 10 logarithm of pi. Now, of course, that in and of itself is not going to be perfect because pi doesn't terminate. And so maybe you'll use 4 or 5 decimals of pi. That will make the approximation good to maybe 3 or 4 decimal places. So when you're interested in computing logarithms with bases that are maybe a little more exotic or that don't appear to parallel the bases you have available, like base E or base 10, then just simply convert to the base that you have that's accessible to you. This is base 10. Now, of course, this would be equal to the natural base of 5.3, and then dividing by the natural base of pi. Either one of these is fine. These are all equal. The change of base is very flexible. But since most students in STEM have access to these bases, then these tend to be the ones that are used most often. Now, of course, there could be a theoretical reason for changing to another base that may be convenient for the particular problem. But again, this is an academic exercise. Here's one more example. Say, for instance, you had this. Say you have the base 6 logarithm of 120. Now, first, when you look at this and you're thinking, 6, that's kind of odd. We're used to base 2 in computers, but we think of, 6 to the first power is, of course, 6. 6 to the second power is what, 36. And 6 to the third power, again, if we look at this is just 6 times 36. So that gives us a 6, carry your 3, 216. Okay, so that's going to be kind of large here. And then you look at 120 and you think, well, what is this? So we've got what? The base 6 logarithm. And of course, there's a 6 here, 6 times 20, right? 6 times 20. So we look at that and we're thinking, okay, we've got use the product rule. So we have the log base 6 of 6 plus the log base 6 of 20. Okay. Now when we look at this, of course, we've got the first power of 6 and then we got the second power of 6. So we've got a number here just like up here, where we would have a logarithm base 6 that would be between 1 and 2. Of course, 6, notice here we have 6 as a lower bound and 36 as an upper bound. So again, we've got the first power here, and let me just go ahead and write this as the squares so you can see the logarithm. That would be much more helpful. And so you could see that the base 6 logarithm for 20 would be between 1 and 2. And of course, this is just a 1. So you're looking at maybe 2 and some change. Okay. So you don't have to, if you're trying to help your client with an estimation of what the base 6 logarithm would be, that may be very helpful for them. So just like with this one, you would be able to ascertain a good estimate. And then if you actually convert to maybe base E or base 10, you would be able to look at the actual estimate that you get and know whether it was in the right ballpark, so to speak. So this gives you an idea of where this lives. So now say we wanted to convert to base 6, or from base 6 to one of the new bases, let's say base 10. So we'd have base 10 logarithm of 120 divided by the base 10 logarithm of 6. That would be a way to go. Or we could do the natural log of 120 divided by the natural log of 6. Again, any estimation you would do here would be reflected here. So change of base doesn't necessarily mean that you're looking for a number. It just means that you are converting to a base out of convenience. Maybe you only have base 3 tables that are available. I mean, maybe that would be a very strange situation, but you simply want to convert to a base that you have access to, or you may want to convert to a base that would be necessitated by a particular problem. Just remember, change of base is to assist you with solving a problem. So don't think that you can't be creative with deciding on how you want to use it. Just remember, the identities for the logarithms are to empower you to be able to solve more problems. So keep that in mind as you work through these exercises. Now, of course, in the next lecture, we're going to talk about how we can use these actual properties, ladies and gentlemen, to solve equations. Because now you're thinking, if we compress all the logarithms to one logarithm, then we can apply the toggle, and then we can actually solve the equation using that. Again, you might be thinking, maybe we don't need to apply it. It just really depends on the type of equation. So we're going to use these ideas we've developed here and apply them to solving equations. So we'll do that next time. Thank you very much.